What is Heron's fountain? Heron's fountain is a hydraulic apparatus that demonstrates the principles of hydraulics and pneumatics. Flow of water from high gravitational potential energy to low gravitational potential energy causes a fountain to form due to increasing pressure on the inside of the system. Pneumatic systems are commonly found in dams, transmission systems, and power stations. Procedure of Heron's fountain. Apparatus needed: straw, bottles, scissor, ruler, marker, hot glue gun, screwdriver or driller.
As water is poured into container 1, gravity pulls it down into container 3. The air filling container 3 is displaced by the denser water flowing down from the top and rises up through the tube connecting container 3 to container 2. This air increases the pressure in container 2, which displaces the water that was previously occupying space. Because the pressure in container 2 is greater than atmospheric pressure, water will flow up the tube and form a fountain. The flow of water will stop once container 2 is empty of water. All of water in container 1 will drain to container 3, and there will be no longer a pressure that was exerted on the system, driven by gravitational potential energy acting on container 1. While container 3 completely fills with water, container 2 loses all its water through the fountain and will fill with air. Once the level of the water in container 2 is below the level of the tube that connects container 2 to container 1, the fountain will stop. If you continue to pour water into the first container, the water level will rise up through container 3 and 2, following Pascal's theory of communication vessels. Because the pressure is related to the height of the column of fluid, the tube leading from container 1 to container 3 needs to be completely filled with water for the fountain to run well. If there is a slow trickle of water out of the top container into container 3, even though there may be a large vertical distance, the fountain will not work well because there is not a continuous column of water that adds to the pressure of the system.
As we know, the containers are airtight, so there must be equal flow of water into the system as out of the system. In conclusion, a bigger effect will be seen when the distance between bottle 1 and 3 vertically is the greatest. In order to change the size of the fountain, we need to raise the level of containers. In addition, we can also change the diameter of bottle, or using different temperature of water that can affect either velocity or flow rate of the fountain. For example, by changing the diameter of tube, a smaller diameter tube will mean a higher fountain and a longer run time. Meanwhile, the larger diameter tube will lead a shorter fountain and shorter run time.